I'm Al Schriesheim. I'm the president of the Chicago Council on Science and Technology, or host, former director, Argonne National Laboratory. We are the Science and Technology Council, an organization dedicated to raising the awareness of the importance of science and technology in our society, getting information on critical issues on science and technology from people who know something about the subject. I encourage each one of you to join the organization. We are a member organization, and of course we depend upon members such as you. Also, you should have received a card which I ask you to fill out that gives us information on how you like the program and what kind of programs you'd like to see in the future and who you are. It's very helpful to us in designing future programs. Well, it's a pleasure for me to introduce George Crabtree. George is a member of Argonne National Laboratory, also the University of Chicago. He is a distinguished fellow at Argonne and has achieved considerable notoriety, so to speak, since I left. The topic of the evening is sustainable energy, fact or fiction. And it, of course, is a subject which is high on the list not only of the region and the country, the world, the production of energy in an environmentally benign fashion, sustainable energy, dealing with the issue of replacing fossil fuels, if that's at all possible, not today, sometime in the future, and covering issues that deal with the critical sticky points in what needs to be done in order to accomplish this, covering the input of the recent, well, not so recent, but certainly the development of nanomaterials and their position in this particular arena. So you all have George's background. The one thing, among other things I dislike doing, is simply reading the background of the speakers. So you are perfectly capable, since you're sitting here in the audience, of reading George's background. Suffice it to say that he is well known, and it's a privilege to turn the podium over to George. George.
Okay, buddy. Well, it's a real pleasure to be introduced by Alan. We've been associated with each other for a long time when he was director at Argonne, and of course I was there. And I have to compliment Alan and this organization, Chicago Council on Science and Technology, for the mission it's undertaken, which badly needs to be done. I think we all need to be more aware of what science and technology means for us in terms of innovation and in terms of economic development and the word of that's so important today, creating jobs. So I really compliment him and Ben and the rest of the staff for organizing things like this. So I want to tell you about sustainable energy, fact or fiction. That's the title. And I want to challenge you to think about what sustainability means. So we know that we love sustainability. right? How can you not like it? What does it really mean, and how do you know if you're sustainable, and how sustainable should we really be? So that's what I'm going to spend the middle part of the talk. You see the second bullet, what is sustainability? But I want to motivate that with the challenges. There are really three of them there. Well, there are many challenges, but I've taken three. Oil, the economy, which is big news now, and let's say was not 5 years ago when we first started talking about sustainability, and carbon dioxide. And then I want to talk about the third bullet, sustainable energy alternatives and roadblocks. Why aren't we there? Why haven't we already done this? And what remains to be done? It will turn out that a lot of basic science and materials research and nanotechnology, as Alan mentioned, will be very important. And then finally, a little bit about the UIC Summer Institute, which is coming up. So let's start with the problems. And here's the first two are on this slide. So dependence on imported oil. So here's a graph of the oil production of the United States, that's the lower curve, and the consumption of the United States, that's the upper curve, since 1950. And you see back in the good old days, we produced about as much as we used, and everybody was happy. Oil, therefore gasoline, was cheap, and we sort of used it freely. Then about 1970, an amazing thing happened. The production of the United States peaked, and it's been going down ever since, and that curve is not going to change. It's going to continue to go down. There will be ups and downs, and you see ups and downs there. Discoveries are made, production goes up, but it's never going to return to the levels that we had before. Meanwhile, our consumption has gone up, and it's gone continuously up, except for a couple of notable valleys there, which have to do with the first oil crisis and the price of oil in the 1980s reaching something like $90 a barrel, which is about the price it is today. And an amazing thing happened. We used less. So here is proof, in a sense, an experiment, that price makes a difference in use. And that's a point I want to return to a little bit later. But then things got better in the late 80s and early 90s. The price of oil went down. We continued to consume. And you see, except for the recession marking starting in 2008 and 2009, when things flattened off, that curve continues to go up. So what does that cost us? So let me dwell for a moment on the dangers of so much imported oil. In 2008, before the recession, 60% of the oil that we used was imported. And that means that the supply is somewhat uncertain. Some of that import is from Canada. That's a kind of a trusted neighbor. But a lot of it is from places in the world that are not so friendly to the West, and in fact that you don't think the supply line is necessarily so reliable. So it could be interrupted by a lot of things. It could be interrupted by a weather event or a geologic event, an earthquake, a geopolitical event, just a decision by some country not to sell oil to certain other countries. And the potential disruption to our society is huge. 2/3 of that oil, whether it's imported or not, goes to cars. So cars and oil are a connection that you should make in your mind. And can you imagine what would happen if we couldn't drive cars or trucks because we couldn't get the oil we needed? So it would be a serious disruption, and it would be a disruption not only to the sort of security of the country, but also to the economy of the country. So that's the first thing. And the second thing is there in the upper right-hand corner. If you just take the number of millions of barrels of oil that we import, and you know the price of oil, let's say it's $100 a barrel, turns out to be $350 billion a year that goes offshore to other countries, does not stimulate our economy, does not create jobs here, but does stimulate the economies of other countries. And we need that badly. You may remember in 2009, the stimulus package was $787 billion, about twice this. So this is half of a stimulus package that goes offshore every year. And that's something that you may have different opinions on this, but many people would say we can't afford to do. So the obvious answer to that is to find alternatives to imported oil, and I've listed a few here. Biofuels, electricity, solar fuels, and there are others that we'll discuss as we go along. So that's the first problem, the dependence on imported oil, and the second problem, the economic cost of fossil fuels in the way we operate now. Here's the third problem, greenhouse gases and climate change. And I've shown here on the left data from the latest IPCC assessment, that was 2007. It's simply data. It is not a model. It's not a projection into the future, so you can see what's happening. And very clearly, the global average surface temperature is going up. And you see from, about 1900, and especially from 1950, the trend is unmistakable. It's hard to say that we're not in a period of global warming. We are. This is data. It's just simply measurements. There's really not much to dispute. Another sign of that is the global average sea level. So since before 1900, that's been steadily going up, and you can see the trend there for your own eyes. Here's a third one, not so obvious, the snow cover in the northern hemisphere. So pretty flat until recently, but there's a very clear trend down, and that trend has accelerated in the last 5 or 6 years. Where do the greenhouse gases come from? Most of them come, 2/3 of them come from these two sources. Burning coal to produce electricity. So more than 50% of our electricity comes from burning coal, and most of the rest comes from burning gas, another fossil fuel. And the exhaust pipes of cars. So there is Los Angeles Basin at sunset, and although it's very red, so you can't see the carbon dioxide, what you see is the pollution that comes out of cars' tailpipes, and that, in a sense, is a proxy for the carbon dioxide. So we know where it comes from, and we have to think about how serious that is. So in the last, let's say, 5 years ago, global warming and carbon emissions were taken much more seriously by a larger percentage of the country than they are now. You may think that's a political reaction to, let's say, the high cost of doing something about carbon emissions or the potential disruption to business that that would cause. Or you may think of it as a political point of view, but nevertheless, it's a fact that fewer people are now supportive of the idea of global warming and of doing something about it. Nevertheless, it's potentially very serious. And in that yellow box, I've shown some of the things that might happen. Permanent changes in weather patterns, in agricultural networks, and in coastal geography. The impact could be rather strong. And this statement, which doesn't always get universal agreement, the cost of accommodation after it happens may be higher than the preventive cost of reducing emissions now. So those are the challenges, and I'm not trying to think for you. You make your own minds up about how serious these are, and these will come up again in the rest of the talk. But now we've known about these since the first oil shock, at least in the 1970s, and we've been thinking about them. We haven't done a lot. So why haven't we already solved this problem? And I think the answer is simple. It's right there in yellow. Fossil is cheaper. And most people, individuals, households, businesses, governments, they make their decisions based on economics. So because fossil is cheaper, that's what people do. And there's maybe some nuance to that statement, and there it is. Sustainable energy technologies are in their infancy. They've been around basically since the 1970s or 60s. That's when we started to work on them hard. Of course, they've been known much longer than that. They perform far below their ultimate potential, so there's headroom there to make them more efficient and therefore cheaper. So there is a chance that the sustainable energy technologies will compete with fossil. However, dramatic improvements are needed. So incremental tuning of the present state of the art for sustainable energy technologies won't do the job. You may get a 10% improvement. That's not going to be enough to compete seriously with fossil. And here is what is needed, and this will be one of the messages of my talk, that we have to understand and control materials and chemistry at molecular and nanoscale levels in order to make these sustainable energy technologies higher performing and lower cost. So I was going to ask you and challenge you to think about what is sustainability. So I'm going to offer you 3 criteria for sustainability, each one harder to achieve than the one before, and ask you to think about, is that what we mean by sustainability? So here's the first one. Lasts a long time. So oil in 1900, we didn't even know how much oil we had. It was cheap to get out of the ground, and we used it freely. We're now finding that indeed worldwide supplies of oil will eventually reach a peak. There's an argument about when, but certainly within a few decades. Some say much sooner. And it's not so freely available as we thought. You might think the same about coal in 2010 or 2012. Plenty of coal, 300 years. Why worry about it? Just simply use it. We may find that indeed the supply of coal isn't that plentiful as we thought. So that's the first criteria. What's the second one? Does no harm. So I've listed 2 things here, nuclear electricity and corn ethanol. I put ethanol, but I mean corn ethanol. So nuclear electricity doesn't produce any CO2. That's a good thing, and that could have quite an impact on the environment and global warming if we ramped up the rate at which we produce electricity with nuclear. On the other hand, it does produce spent fuel. And what do you do with that spent fuel? That's a good question. At present, a political question as well as a science and technology question. And you have to balance, depending on where you are in the debate about nuclear energy, you'll feel one way or another, that one or the other of these problems is more important. Corn ethanol, again, like CO2, doesn't produce much. Like nuclear electricity, doesn't produce much CO2. 5 years ago, we thought that it could be maybe even close to CO2 neutral. We've now learned by doing careful life cycle analysis and looking at corn ethanol in detail, that its footprint for fossil fuel and for CO2 emission is not that different from gasoline. It's a little bit lower, but not substantially lower as we once thought. So most of the world now believes that it's not a solution to the CO2 problem. Nevertheless, it's been written into policy and into the law, and we're going to keep producing corn ethanol in this country and elsewhere for a long time, even though it's not necessarily the best solution. Now, there are other ways to produce ethanol from biofuel, so cellulosic ethanol, and we'll talk about that. It may be a better bargain. What's the third criteria? It's the one that's the hardest to achieve, but I think you'll agree really means sustainability, leaves no change. So it means you close the chemical cycle. So all the inputs to the energy production process and all the outputs that it produces are recycled back to become inputs. So leaves no chemical change. And I've listed 2 energy carriers there, electricity and hydrogen, which at least are capable of achieving this goal. So let's think for a minute. Here's our sustainability criteria. Do we have any technologies now that we can deploy that satisfy these criteria? And in fact, we do. And you're all familiar with at least one of them. That's this one, solar electricity from photovoltaic cells. Think about this. There's the semiconductor photovoltaic cell. A photon from the sun hits it, excites an electron from the valence band to the conduction band. That electron goes through some wires. It does some work for us, and electricity can do quite an amazing amount and diversity of work. Some of the things are listed there. The spent electron comes back through wires. It replaces the hole, which was originally created in the solar cell, and nothing is different. So you can't tell that that work has been done. Now, there are a couple of caveats to that. The first one is that there is one difference. There's one less photon in the sun. And the sun eventually is not infinitely long-lived. It will run down. It's been here about 5 billion years. It'll probably be here about another 5 billion years. But in the technical sense, it's not fully sustainable. Nevertheless, that's a pretty good record, so we're going to take that as one of our reference points. And there's another caveat, but before we do that, let's take a look. Does this satisfy our criteria? Does it last a long time? Yes, 5 billion years, pretty good. Does no harm? Yeah, that's true. Leaves no change. It seems to be a fully sustainable energy chain. But there's a second caveat. You have to build the infrastructure that carries that number one, the solar cells, and it carries the electricity. That costs energy. That produces CO2. So the construction costs and the end-of-life costs have to be taken into account, and they're not fully sustainable. What do we need to do? Well, we need breakthroughs. So in spite of the fact that the best solar cell you can buy now is about 20% efficient commercially, we need to do better. So we need lower cost, higher efficiency photovoltaics. These are sometimes called third-generation materials and nanostructures that are going to enable that. So we need that kind of materials research. And very importantly, electrical storage. If you have 50% of your electricity coming from the sun, you have a problem at night. And so you have to find a way to store. There are other things you can do, some other technologies. Carbon sequestration is one that gets talked about a lot. Here's the energy chain. So here's pretty much how you mine coal. You do it from the surface because that's the cheapest way to do it, and it's easy. Hundreds of years of resource. Burn it in a fossil fuel plant to produce electricity. But instead of emitting the carbon dioxide to the atmosphere, you capture it. And you put it underground somewhere. So in a cavern, a geological formation. And you have to keep it there for a rather long time, thousands of years. Why? Because the ultimate sink for carbon dioxide in the atmosphere is the deep ocean. And although the exchange with the shallow ocean happens every year and is rather quick, the exchange with the deep ocean takes a long time because it's basically the time required for one cycle of the conveyor belt currents in the ocean to go from the Pacific to the Atlantic, to the north, to Greenland, and back down to the equator. The time to complete one of those conveyor belt cycles is 400 to 1,000 years. And you have to wait several of those cycles to take the atmospheric CO2 to the deep ocean. So you have to trap the stuff that we're producing now for thousands of years. And that's a challenge. So will it leak? You don't know. Think about this. If you have a leak rate of 1%, then in a century, all of the CO2 that you stored in the first year has leaked out. And a century is the blink of an eye in global warming terms. So you have to keep it for a very long time. What will it do? What will this carbon dioxide do underground? Well, it reacts with rocks. And though it reacts at high pressure and at high temperature, unlike on the surface. And we don't know what those reactions will be. Some of them are very favorable. Some are potentially unfavorable. There are about 12 or 15 different rock environments underground where you might store carbon dioxide, and you have to know what the reactions will be with all of those. So that's an unknown. It's a little bit like we thought, let's say, over the last 50 years. The atmosphere is big. Let's put all the CO2 in the atmosphere. It can take it, no problem. We're now realizing that although it's only 390 parts per million that we have there now, it's already causing a problem. And that's kind of the same situation for carbon sequestration. You put it underground, you don't know what will happen. There could be some harmful effects. So the rocks down there are porous. That's why there's room for the CO2. That means the CO2 can migrate. That means it may go miles or more in the time that it's stored and pop up somewhere where you don't expect it. So how does it look? Lasts a long time? Well, hundreds of years. That's good, but that's not as good as the sun, so that gets a neutral face. Does no harm. It's sort of a dichotomy there. No CO2 emissions. That's great. On the other hand, you have to sequester the carbon dioxide underground. What does that do? We're not so sure. And leaves no change? Absolutely not. You're taking coal out of the ground and putting CO2 under. So there definitely are chemical changes. Here are some of the breakthroughs. I've already mentioned them. What's the chemical reactivity with rocks in extreme environments, high temperature and high pressure? Migration. You need to have geologic monitoring from the surface to figure out what that stuff is doing. And predictive modeling. You need computer programs. And And what about leakage routes to the atmosphere? Here's another one we've already mentioned, nuclear electricity. You mine uranium about like you mine coal, so you do it from the surface. And like coal, there are hundreds of years of fuel there, no CO2 when you burn the fuel in a nuclear reactor, but you do have spent fuel. And you have to put that spent fuel underground, not unlike carbon sequestration, where you have to store it for a longer time, so tens of thousands of years. And depending on how you do it, it might be a longer or a shorter time than that. You don't really know what will happen to it. It's hard to guarantee that anything will be secure and safe for that time scale when you think that civilization itself is only about 10,000 years old. So how can we guarantee what will happen to it going forward? So here's a picture of Yucca Mountain, which is now off the table thanks to the Obama administration. But it's basically a tunnel, you see it there, and casks of concrete or some other hard storage, inside of which is the spent fuel. It's about 300 meters below the surface to keep it out of rain and other water that comes down. It's 300 meters above the aquifer to make sure it doesn't affect the aquifer. And you hope that it'll be stable there. So there are lots of challenges. Here are, well, let's first do the profile. Lasts a long time, about the same as coal, not as good as the sun. Does no harm, and again, a dichotomy. So no emissions, that's great, but what do you do with the spent fuel? And it very surely does leave a change, taking uranium out of the ground and putting spent fuel back in. Here are some of the things that we have to, the breakthroughs that we need in order to do this. All of the nuclear reactors that we use now, or most of them, were designed in the 1960s. So it's old technology. We can do much better now. And if you're going to deploy suddenly at a higher level, you want to put out the best reactors that you can. So you need materials for higher temperatures because you'd like to raise the temperature, make them 50% efficient instead of 34% efficient as they are now. That means you have a higher neutron flux, and you need materials that can withstand that higher neutron flux and the higher temperatures. It's very corrosive at those temperatures. Even water is corrosive at those temperatures. And like for carbon sequestration, geologic monitoring and modeling is needed to know what will happen to that spent fuel underground. So as I said earlier, depending on where you sit in this nuclear debate, you'll have different opinions about what's more important. But this is a sustainability question that we have to answer eventually. So what about conventional oil? Well, you don't have to use conventional oil for your car. You could grow biofuel. So here's switchgrass. That's how much it grows in 1 year. It's quite impressive. And you'd like to take the roots and the stalks and the leaves, the cellulose of that switchgrass, and turn it into ethanol. So here's an ethanol plant. This happens to be a corn ethanol plant, but cellulosic would look about the same. You would burn that in your car. The CO2 would come out of the tailpipe and go into the atmosphere, but be recycled back over 1 year to create and be embodied in the next year's crop of switchgrass or whatever energy crop you have. So that's a great idea. And there's lots of work going on now to develop cellulosic ethanol. It's a tough chemical problem. We don't know how to do it. Right now it costs about twice as much as corn ethanol, and that's too much to really be competitive. So lots of research going on that may in fact solve that problem, but that's what remains. So you don't actually, there's another opportunity here. You don't actually have to use plants to do this, so you could rely on biology. But by solar fuel without biology, the second line there, you can do what nature does, but do it artificially. So artificial photosynthesis, chemicals out of the lab, which do the same thing, split water and reduce carbon dioxide to make fuel. You can do it using photons from the sun, the energy of the photon, or the heat from the sun, either way. And less research is going on for that, I would say, than for cellulosic ethanol, but still quite exciting and quite advanced. And there's a third opportunity. So conventional oil, light sweet crude, you don't have to use that. There's lots of heavy oil, unconventional oil. So oil sands and oil shale, a lot of it in western United States and Canada, or even coal to liquid. And we know how to do that. That technology is around. It's expensive. It gets to be economic at about $80 or $90 a barrel for conventional oil. And that's where we are now, and I think companies may want to start doing this, but they want to be sure that the price will remain high. So they're a little bit reluctant to start. There is a downside, and I've listed it there. 50% more carbon dioxide is produced to make a gallon of gas from this heavy oil because it has lots of carbon in it. And so you're going to be putting out more CO2. And of course, there are more nasty, toxic pollutants associated with the oil sands and shale than with conventional oil. So how does it look? Well, here's the profile. Lasts a long time, does no harm, leaves no change. With cellulosic and solar chemical fuel, it's possible. So not there yet, but that's certainly on the horizon. If it's oil sands and shale or coal to liquid, it's a different story. Lasts a long time. Well, the resource of heavy unconventional oil is maybe about the same as conventional. So you'll get a factor of 2 more life out of it. That's good. But not as good as the sun. Does no harm? No. You're producing more CO2. And leaves no change? Again, no. So you're altering the chemistry and the geology of the Earth. What do we need to make this work? They're right here. We've already mentioned them. Cellulosic breakdown of sugar to sugar or fuel, and the chemistry of carbon dioxide to fuel, which is another tough challenge. But certainly we have the example of biology, which knows how to do it, and the proof of principle that it can be done. You don't have to run your car on oil at all. Why don't you run it on electricity? So you could electrify transportation. There are 2 routes to electrification shown here, upper and lower. There's the essential thing that replaces the engine. It's an electric motor. Boy, is it efficient. They could be 90% efficient, typically are, sometimes higher. That's the motor that runs the Tesla. There's no scale bar there, but it's a thing like this, not very big. And is it ever simple? It has a shaft which turns on the inside. Everything else is stationary, and there's some coils that produce the electromagnetic force. It's very appealing. So if you were going to start now to make a personal transportation device, a car, you might ask, should I do it with batteries and electricity and electric motors, or should I do it with an internal combustion engine? So an internal combustion engine is about maybe 25% efficient versus 90% or more for motors. There's a big plus. You can make electricity in lots of ways. We'll describe 2 of them here. But if internal combustion engine, you pretty much need gasoline and oil. So if you're going to run your car on electricity, let's look at the upper route. You can store the electricity on the car in a battery. That's already a problem. Batteries are not good enough to drive very far. So you might go 40 miles or 60 miles or 100 miles in Chicago winters. You probably wouldn't go quite that far, and you need to recharge them. So battery technology is a breakthrough that we need, higher energy density. You have to get that electricity from somewhere. You would charge from the grid, probably. And that means, where did you produce it? If you produced it by burning coal, you've produced a lot of CO2 to make that electricity, and you have to do an analysis to ask, have you really helped the CO2 problem? In this area, where there's a lot of nuclear, almost 50%, you certainly would save on the CO2. In other places that are pretty much coal-driven, you may not. So if you take the lower route, and this was popular in 2003, you make the electricity on the car with a fuel cell. What does a fuel cell do? It takes hydrogen, splits it at the anode, and ionizes it, sends the electron through some circuit, which runs the motor, collects the spent electron at the cathode here, where it meets up with protons, which have gone through this membrane inside the fuel cell, and you create water combined with oxygen. So that's a complicated chemical reaction, and we don't really know how to catalyze it well enough yet. So the problems here are basically catalysis and electrode design. You'd have to store the hydrogen on the car. That's still a problem. We don't have materials yet that are viable for that. And you have to produce that hydrogen somehow. So you'd like to do it renewably. If you do it by converting, reforming natural gas, which is the usual way, Turns out you produce exactly as much CO2 as if you had burned the gas directly. So you haven't really helped that problem. And you need a whole infrastructure to make this hydrogen cars and transportation work. What's the profile? Well, it looks pretty good if you're optimistic. So you could satisfy these criteria. You need breakthroughs, so 2 to 5 times higher energy density in batteries. And you need catalyst membranes and electrodes for fuel cells. We really don't have these things under control either, so there's still research challenges there. So those are the technologies and the breakthroughs. Now I want to talk about 2 enabling technologies that need to be done if these are going to be deployed on a large scale. And the first one has to do with the electricity grid. So here's what the US looks like at night from space. You can find this picture. It's quoted. It's shown a lot. You can find it on the NASA website. And you see where the electricity is being used. Those are the nice bright white spots. And you realize that what a wonderful engineering accomplishment the grid is. In fact, the National Academy of Engineering called it the greatest engineering achievement of the 20th century. Because it's so big, you can see it from space. It brings electricity where you like. You're out in the countryside somewhere and you say, I want to have electricity. The power company brings you a cable no bigger than this. You can attach that cable to whatever energy devices you need. And you can put a switch in it to turn it on and off at will. It's really wonderful. But there are some problems going forward. So that was the 20th century. This is the 21st. So what are some of the problems going forward? Well, think about this. Where is all the wind? Where's the best wind resource in the country? It's somewhere down the middle of the continent. It goes even a bit further south than I've shown there. Where is the sun? It's in the southwest. Lots of sun there. Where are all the people? They're pretty much east of the Mississippi. And you have to get all that renewable electricity, if you're going to tap into this wind and solar resource, from its source to market. There's also a sliver of people living on the West Coast. Either one is pretty far away. So thousands of miles you have to transport. And our grid is not made to do that. So our grid was made to serve cities and towns with a power station that might be 10 miles away or as much as 100, and bring that power in, but not to send power in large quantities across the country. So this is a little bit like the highway system before the interstates. You could drive from New York to Los Angeles, but it was painful. Took a long time. There were potholes. You know, it wasn't pleasant. We need to make an interstate highway system for electricity if we're going to exploit this renewable resource. And there are lots of not only technological questions, but political questions about how to do that. So here's the breakthrough you need in very large terms: long distance, reliable, efficient delivery of electricity. One more technology, and I find this one very interesting, and that's storing energy. We have to learn how to store energy. A couple of reasons you might want to do that. You might want to drive your car on a battery or on a hydrogen fuel cell and store some energy, as we do in a gas tank, on the car. Or you might want to have wind and solar power providing your electricity, and you need to make up for the fact that it's intermittent. So here's a plot of the energy density by volume and by weight of various storage media. And you see on this plot where gasoline is. It's way up there in the right-hand corner. It's wonderful. It stores energy in chemical bonds. And those chemical bonds, when you break them, usually by combustion, release their energy as heat, and you turn that energy through some kind of a heat engine or an internal combustion engine into motion. And you might want to turn that motion into electricity with a generator, or you might want to use that motion just to drive yourself down the road. But the energy storage capacity of gasoline is wonderful. That's why we drive around with gasoline in the tanks of our cars. On the same scale, there's batteries. That's the best battery you can get, the best lithium-ion battery you can get now. And you see the gap is huge. And that's one reason why the battery challenge is so great. Now, it's not as bad as it looks because, as you remember, Gasoline engines are 25% efficient, and motors are 90% efficient. So you don't have to produce as much. You'll cut that gap by some, but it's still quite strong. So what do visionary scientists and engineers say? They say, maybe you could make batteries 10 times better, that is, store energy at 10 times the density. Lithium air instead of lithium ion. And that blue thing there is the region of 10 times better. It's still far from gasoline. But there is something. Think about this now. Put something at the bottom here. What's so good about gasoline is that you store energy in the chemical bond, so chemical storage. And what's so good about batteries is that you use the energy as electrons. So what you want is some way to store energy chemically, but use it not through combustion, but through electricity. And there is a way to do that. That's illustrated here. So it's electrochemical storage. So I've shown there's ethanol used, as a sort of as a gasoline substitute. There's methanol. There's hydrogen, which you would use in a hydrogen fuel cell. There's compressed, that's the target. Here's compressed gas hydrogen. And that's better than batteries already. But there are a host of things that fill that gap that let you do what you want to do. Store the energy chemically, but use it electrically. So my personal feeling is that electrochemical conversion offers wonderful opportunities for energy in the future, and we need to emphasize that both in our research and development and in our educational institutions. A good friend of mine at Argonne, Nidad Markovic, tells me that every top electrochemist was trained in Eastern Europe, because that's just kind of the way things went. We need to make that happen in the United States. Here's the breakthroughs, as we've already said. 2 to 5 times increase in battery energy density, or you could get a 10 to 20 times increase through chemical storage plus fuel cells. So now let me talk a little bit about materials and how they're so very different in the traditional fossil economy and from, let's say, the sustainable energy economy. And this I find fascinating. If you think about the traditional fossil energy conversion chain, something comes in, which is a fuel, so it's gas, oil, or coal. The first thing you do is burn it to get the energy out. It comes out as heat. Very often you don't really want the heat, so you convert the heat in with a heat engine of some kind into the useful work you want, that is motion or electricity. The important materials here are the fuels. So you like them because they're cheap and because they have a high energy density. So they're commodities. You don't care really what it is. You want to burn it. You lose it in the first step of the process, so it burns up and it's gone, and you have to go back and find some more. It's very different in the sustainable energy conversion chain. First of all, the input is usually not a material. It's some kind of energy flow that is otherwise unused. So sunlight, wind, water, geothermal, biomass actually is a material, but it gets replenished every year. And you convert not with combustion, but something that you do at room temperature, some chemical reaction or some physical reaction, like a solar cell. So the photon comes in, ejects an electron from the valence band, and you use it. So there's a physical conversion process. And then the things you get out, some of them are listed here: electricity, biofuels, solar chemical fuel, and you get to your useful work much more directly. The important materials here are not the inputs, and they are not commodities. They are high-tech materials in chemistry, like a photocell, that convert the incoming energy stream to useful work without combustion. And those things are at a relatively low level of development. So as we were saying earlier, the best commercial solar cell you can buy is 20% efficient. In the laboratory, you can make, and many people do this, 40% efficient solar cells, so-called multi-junction ones. They're too expensive to think about deploying them. But it shows that there's lots of headroom there for the research and development community to tap into, to achieve, to lower the cost, And that, indeed, would have to be the future. It's really a basic material science challenge, not an engineering one. So this is the bottom line message. Sustainable energy requires controlling complex, functional, high-tech materials and chemistry. That's the challenge we have. So now let me try to convince you that this is the moment to do it. And I've written up there in yellow our goal. That's what we had from the last view graph. And the 3 blue bubbles, which represent opportunities that we have now and didn't have, let's say 10 years ago, to achieve this goal. And let's start with the one in the middle, nanoscience. So 10 years ago, the word nano was not a household name like it is now. We didn't quite know what nanoscience was. After a few years now we do. But we've had 10 years of it. And we've had 10 years of making measuring instruments which can look at the nanoscale, say the atomic or the 1 nanometer to 10 nanometer scale, see what's going on. We know how to make materials from the bottom up by self-assembly or by other techniques that we didn't know how to do 10 years ago. So we have enormous capability to look at that scale that we didn't have before. And that's very clearly the place, the nanoscale, is where many of these energy conversions take place. So if you think about a chemical reaction or you think about a photon being converted into an electron in a solar cell, it happens on the nanoscale. Let's look at the left-hand one, computer modeling. So 10 years ago, we crossed the teraflop frontier, the first machines that could operate at that fast. And now we're crossing, or probably already crossed, the petaflop, factor of 1,000 faster frontier. And everyone says in 10 years or less, maybe 8 years, we'll pass the exaflop frontier. So if you look over a 20-year period, it's 6 orders of magnitude increase in speed. That means that you can model and simulate things that you couldn't think of doing only 10 years ago. So you can model material, you can model millions of atoms instead of just thousands, with first principles techniques, and those millions of atoms, that's a big enough chunk to have some functionality and some complexity and some features, properties that smaller chunks don't have. So you can start to model materials and functionalities in the computer that don't exist yet in the laboratory. So think about this, which you can do now. You could model, let's say, 1,000 different materials that you think might be good hydrogen storage compounds or that might be good catalysts. And you can eliminate on the computer probably 990 of them. You don't have to make those in the lab. Done. Then you take 5 that look promising, you make them in the lab, and let's say 2 of them work out. You've saved an enormous amount of expense, effort, time to get to that point, and that's because of computer modeling. What about the third thing? So complex materials. So think of biology. Biology is the paragon of complex materials. Its complexity makes it functional. That's why you have, for example, a biological cell in which all kinds of processes are going on. There might be 1,000 different chemicals in that cell that turn on and turn off in response to signals. And boy, is it ever functional. That enables life, but lots of other things too. And this is, in a sense, the proof of principle. It tells you that you can make complex materials with complex functionalities, but you have to try hard to do it. So the goal would be, let's have the complexity and the functionality of biology, but done with inorganic materials. And that would be the sustainable energy platform on which we would grow the sustainable energy technologies. So you can read the rest of the slide. I don't think I'll say it. I just have a couple of more slides. I want to give great credit to the Office of Science in DOE, and especially the Office of Basic Energy Sciences. They started in 2002, that's the first report there listed, to hold a series of workshops and bring together, let's say, 100 or 150 scientists for each workshop to examine all the energy technologies. Where are they? What's the status? Where could they go? And what are the priority research directions that are needed to make them blossom? And they didn't stop. So in 2002, energy was not a buzzword. And to show you how long ago that was, the price of oil in 2002 was $28 a barrel. And that was considered high. So times are different. And since 2002, we've been through lots of crises and education and consciousness raising. There have been about 12 of these workshops, and they are now thought to be authoritative snapshots of where we are with each one of these technologies and where we have to go. So it's a wonderful resource. And I think it's done a lot to educate both decision makers in government and the general public, and of course the scientific community, about what is needed. But it isn't only technology, and it isn't only science, and it isn't only materials. It's also making it happen. So there are three kinds of sustainability shown on this view graph. We've been talking about energy sustainability, but it won't happen without economic sustainability, and that, of course, is very much on our minds now. We need to grow the economy. We need to create jobs. We haven't recovered from the Great Recession of 2008, and very often these things are at odds. So if you want the economy to grow, you want cheap energy. And you don't want to do a lot of research for fancy, change the system, make it cost more. You just don't want to do that. So those things there's a tension between them. And then there's environmental sustainability. And of course, in a way, the same tension exists. If you have cheap energy, and let's call it fossil, then you're probably doing more harm to the environment, which ultimately may come back to bite you in ways that you didn't expect or at least didn't want. And you have to think about that tension. So you have to somehow find a pathway that satisfies all three of these criteria if you're going to have a successful technology. And that, I think, is one of the major challenges. So what do we need to do? I'm going to quickly show all of these at once. I think there are four things we need to do. We need to educate the next generation for energy literacy. So that means not only the scientists and engineers, they have to understand all the technical aspects, but the regulators, the government officials, the business people, the urban planners, so that they will understand how do you get to a different energy economy and what's it cost and what are the impacts. I think we don't have that at the moment. And most of all, private citizens, so us. We are the ultimate decision makers. So we had an election recently where a different political party took over the House. That's just a result of us voting. So the decisions really, the big ones and the trends, reside with us. And we should be educated so we understand what we're voting for, and then we should send that message to Congress in order to make it happen. And remarkably, the system works. Right now, it looks a little bit like the system maybe is dysfunctional and there's nothing but political infighting, and to a certain extent that's true, but that's the way our system operates. So we need that. So we need to research and develop. I'm down now to the second big line. More sustainable energy technologies. That's a big effort. Many people say the amount of money devoted to that research and development effort is too small, as much as a factor of 3 too small. And you'll find political policy documents on both sides of the spectrum, left and right, which agree on that. So this is one of the things that maybe will not be subject to so much political infighting. We need policy, so we have to encourage the new technologies that are going to come out, and it's not easy to figure out which ones those are. So we talked already about hydrogen and corn ethanol. Looked pretty good, but turned out not to be the one. So how do you make that decision? It's a tough one. That's technical. And we have to evaluate and incentivize the most suitable options. That's a hard job. And we have to encourage entrepreneurship. As the risk takers out there are probably not going to be big business, at least not initially. Develop a culture of innovation and risk taking. That's what we have to do. And that also affects very strongly our economic position, competitive position against the rest of the world. We've got to be the innovators. So, and then you have to deploy these technologies through small companies, which may get bought by big companies when they turn into successes, but that's, of course, perfectly okay. So I wanted to spend a minute talking about the UIC Summer Institute on Sustainability and Energy. We held this for the first time last August. We had a cohort of about 40 students, and we covered all areas. Those 3 lines there describe what we did: intense immersion in energy and sustainability with distinguished speakers, about 25 of them from around Chicago and around the country, tours on energy and sustainability sites, and student team challenge projects solving real-world problems. And this was, we'll have it again this summer. There's the website. I encourage you to take a look at it. This is my last slide, the perspective, and I think I won't even go through this because it just says everything that I've already said. There is a potential historic transition taking place to cleaner, alternative, and sustainable energies. It will take a long time to happen, obviously. The bottleneck, and this is the central message, is basic science understanding of the materials and chemistry that make up those technologies. So with that, I think I'll stop. Thank you very much. I think there's time for questions. Yes?
I have a slightly different view about the transition taking decades. Just what you look for is what are the limiting factors that can bring the cost down. And if you look at an example, for instance, the plastics are very cheap, but are too cheap because they cause pollution. Why they're so cheap? Because the fluidized beds were developed by chemical engineers which radically brought the cost down. The same situation, I think, can occur with the photovoltaics. A major cost of the photovoltaics is the purification of silicon. Impure silicon sells for half a dollar a kilogram. To purify, you have to increase the purity by 5 orders of magnitude. That turns out to be, that takes only 0.2 kilowatt hours per kilogram, a very small amount. The Siemens process, which is still the one, uses 100 kilowatt hours. Why? Well, it's because it's built by physicists, so it's like a big physics experiment with rods, and that's how we make the silicon, which is fine for computers. The fluidized beds are being developed now, and they talk of 10 kilowatt hours per kilogram. But if you look at the minimum energy, it's 0.2, so you can do a lot better. And one of the things that can do it is develop a good process using fluidized bed technology, which should, looking at history like a plastic, should bring this price down. So I don't see why we need decades. Unfortunately, the basic sciences is not putting any money into the engineering. What happened when nanotechnology came out, when we worked on it, we were the beneficiary. We thank the National Science Foundation for their support, but they took the money out of engineering and put it into the nanotechnology, where hopefully we'll get some use, but the engineering part got cut. And you mentioned, for instance, the computers, which is what science is. That's very good. But engineering, we use computers engineering too in the design. There was a radical shift in how we could do fluidization. You know, we developed computer programs which can design these cells. We don't have to go and wait 2 years for an experiment that may or may not work. So I think there is a tremendous potential. It's a question of recognizing where do you put funds in. Anyway.
So that point of view is one that I can really support. And I think you're saying basically at heart, innovation counts and you should look at all possibilities. And I completely agree. Some are on the engineering side, some are on the basic science side. We should take them wherever they are. And we should develop them aggressively. So I mean, part of it's intellectual, but as soon as you realize this is a good idea, then it becomes money. And you have to have teams, and you have to have sort of a wave taking place. So I fully support that. Yes?
George, I'm interested in understanding the principle that makes you say that a complex nanoscale material is somehow or other intrinsically better than a comparably complex biological material that would do the same thing.
Okay, that's a great question. And I detect where you're coming from with that. You're-
No, I can imagine the principle. I wonder what.
So what I wanted to emphasize was that most of the non-biological materials we have now are relatively simple if compared to biological ones. Steel, actually, has been around for a long time, is actually pretty complex if you look at it. It has a lot of components, and it matters very much how much of each component you have that determines the properties you get. But many materials, that's still rather simple. Many other materials are even simpler. So I come from the superconductivity community, and we are very proud of the fact that we can put 5 elements into a copper oxide material and have it superconduct at, let's say, 90 degrees Kelvin. For us, that's complicated. That's trivial when it comes to the scale of complexity of biology. So my point was that if we could make our inorganic materials, let's say, twice as complex or 10 times as complex, still not achieving what biology achieves, there's a lot of payback there to get. The more complexity there is, the more degrees of freedom there are, the more things the material or the system can do. And I didn't mean to denigrate biology at all. We should absolutely use biology in every case where we can, and that's a kind of a booming field right now, so I mean, I think it is happening.
I think it's probably a trade-off between what might be chemical stability and self-maintenance, something else which a living organism would do in the face of instability. So I actually have trouble figuring out which one.
Yeah, I mean, the fact that living materials reproduce and, you know, when they get old and tired, you just make a new one, and it happens automatically, boy, that's powerful. And there's self-healing as well that occurs. Those are powerful things. I agree. Yeah.
I've got a question. What are the challenges to splitting CO2 into those single compounds?
It's just very hard. I mean, so CO2 is pretty stable. So you have to break it somehow. Yeah. I mean, biology has learned how to do it, plants and so on, and they use photons from the sun of a certain energy, but there's only one way to do it, basically, that biology, nature has found, and it works, but it's a tough job. And if you try to do it in the laboratory by some other technique, it just turns out it's difficult. So it's not a real answer, but it's just because CO2 is so stable. This is one of the issues.
So you split CO2 into single compounds. How does
Yeah.
that affect the equation?
Well, you would split CO2 into CO plus O. That would be the first thing. And then each one of those is reactive, so you could use the reactions that those enable to go through another set of reactions. And eventually, plants produce sugar. I mean, that's their fuel. We'd like to produce, let's say, methane or something that's simpler and that we can use more or less directly in our energy system. And that, in a sense, the phase space, the number of choices is huge. You've seen these diagrams where there are lots of reaction pathways, and you really don't know a priori which one is the best one. So people are starting to recognize that it's worth going after that problem. But for a long time, people said, oh, that's too hard. Let's not do it. And it's going to take the funding agents, actually, to recognize that it's a good problem.
If you want to get energy out, see if you can put it in.
Yeah. And you have to get it from some. And the sun is sort of the best candidate, right? I mean, everything else is a piker by comparison. Yes?
I have a couple of questions. One is solar energy, one is hydrogen. We're having this new energy institution called JCAPS. I heard
Yes.
Dave Lewis, he was talking about bypassing the national laboratories and bringing the solar energy online quicker. But is the private sector cooperating with the JCAPS and we possibly be able to have that be an efficient way to get solar energy online if you don't have the private sector collaborate? The second question on hydrogen. I understand that in the European Union, they're building lots of hydrogen filling stations because this materials engineering in Denver, LEDs are from Denver, has developed a method of controlling the use of hydrogen in glass capillaries. They're going to test drive these hydrogen vehicles in the European Union. I haven't heard anything more about it. I'm trying to get information. But the question is, now that we're doing that in this country, and then we have to, of course, produce hydrogen in a carbon neutral way. Take Gray of Caltech with his innovative catalysis method. tests in the United States, which the European Union is doing, and also trying to build that infrastructure for hydrogen. So it seems to me we're very negligent in this country in that area. I'm hoping the JCAPs will work in the other area. What do you think about that?
Yeah, so you had two very good questions. I was asked to repeat that. Yeah, I was asked to repeat the question. Let me see if I can read. You correct me if I don't repeat it correctly. That JCAP, which is the new energy hub that Nate Lewis and Caltech is heading, in order to get solar fuels, so it's both artificial photosynthesis and photoelectrochemicals, things that PV, could it get to industry faster and promote solar more effectively than we're doing now? I think that's something like your question. That's what he claims, yeah. Yeah. So a couple of comments on that. First of all, the price of solar has gone down dramatically in the last few years. And you'll find various reasons why. The recession may be one of them. The competition from China, which is able to have a huge workforce that's not paid very highly, is another one. And that has actually prompted BP Solar, you may have seen this in the news a few weeks ago, to get out of the solar cell business. They've said we can't compete with China. And prices have fallen something like 50% if you look at the numbers. So prices are coming down. Now that isn't quite the same challenge that JCAP is facing. So what we really want is to have higher performance solar cells, either through artificial photosynthesis of a fuel or just photon to electron. And can they do that? Industry is in a strange place here. So industry never wants to take a chance that it's not pretty sure is going to work out. And you'll see in the solar industry, like BP Solar, folks that did step out on the limb are now, some of them, getting burned and deciding to quit. So you need some kind of intermediate high capacity and high, let's say, capability system to take that charge on. And I think what Nate wants to put together is a consortium which have some national labs in it and some industries that are willing to do that, and that is highly and strategically put together in a way that it will work. So this is what needs to happen, and whether Nate will succeed or not, one doesn't know. I mean, that's a high risk. It's much higher risk, I think, than batteries. So in a sense, it belongs there to be funded by somebody other than industry. Your second question is, why don't we do more with hydrogen? So Europe is doing things with hydrogen and we aren't. I've simplified dramatically, but I think this is the bottom line sense of your question. So hydrogen was really popular in 2003. President Bush said, babies born now, their first car will be a hydrogen car. Well, we know that's not going to work. It's just going to be farther away than that. And I believe, partly for political reasons, but for other reasons too, you don't hear much about hydrogen in this country. That doesn't mean that the car companies are not doing it. In fact, they are. If you go to GM and Ford, they have big hydrogen programs which have been around for a long time and haven't really reduced much in the last 5 years or last 3 years, in spite of the fact that the government is not funding hydrogen through DOE and NSF at the rate that they were, not anywhere near. So there are other reasons for that. My feeling is that that will come back, that hydrogen has something to offer. It's farther away than electric cars with batteries because they don't have infrastructure problems and so on. And that was the right decision to go with electric cars by battery before hydrogen. But in 20 years or in 30 years, there may be an opportunity there, and I don't think we should throw that away. So Europe didn't suffer the ups and downs that the United States did, both the up and the down when it comes to hydrogen, and they're still kind of coasting along at the rate that they were. That was a long answer to that. Sorry. Yes?
Near the end of your presentation, you mentioned the role of public policy in spurring alternative energy R&D. I'm wondering what your views are on carbon tax and rebate as a way of leveling the playing field between fossil fuels and alternatives.
So that's a good point. I said very early in the talk that fossil is cheaper. And many people would say it's not cheaper if you fold in all the externalities, all the costs that the fossil companies don't have to pay. So the cost of global warming, or the cost of emitting mercury, or the cost of emitting something else. Your question is, should policymakers try to either present a tax or some other system, cap and trade, that folds those costs in. And I don't make policy, and I think there's an enormous change going on now, even a fluctuation from left to right to left, maybe. Let's see what happens. But we're not sure what we think about that. The recession colors the way everyone thinks now, and anything that's expensive, maybe we should put off and not do. 5 years from now, there may be a different attitude completely. And to me, that's a little bit unpredictable. But if you want to deal with this problem, if you're serious about carbon emissions and global warming and the cost of fossil, you should do that. And there would be a tremendous political barrier to getting that done. We've seen that in the last 2 years. And I'm not sure how you would get past that barrier, or if you can. It would take a lot of private citizens like us being fully literate and educated and having, let's say, authoritative opinions on what should be done to tell our congressmen, listen to us private citizens more than you listen to, let's say, special interests. And whether that would happen or not, I don't know. But I think you've raised an issue. Yeah.
You mentioned your project at UIC.
Yes.
It seems to me the hope for all of this are the students that are now in school and high school. What do you see? I mean, do you see an increase? I mean, how do you judge students right now? Where are they? Is there hope there?
So just to repeat your question, the next generation that's in high school and early college now will be the ones to implement this stuff, and what do we think about those students? And my sense is that there's a tremendous interest there. So this happened, I guess, 5 years ago, maybe 4 years ago, that for physicists, the big meeting is the American Physical Society meeting in March. We held a workshop for 80 students. You had to apply, 150 did, 80 were accepted, to talk about energy research and how to break into that business. And that was the most lively workshop, I was one of the lecturers, that I have ever been to. I mean, there was buzz in the room everywhere. And everyone had the same question. I got the question, this was a common question. I'm doing high energy physics now, but I want to do sustainable energy physics. How do I do it? How do I break in? And there wasn't an answer at that time. Now there is an answer, because in a short period of 5 years, there are lots of research opportunities for those who want to do that. There are lots of public policy opportunities for those who want to do that. And we're having that workshop again. It's happened every year in February this year, and we're going to announce some of those opportunities. So I believe you're right, that it's going to happen by kind of a changing of the guard, and that may be a couple of decades, or let's say 10 years, before people become comfortable with that and the new attitudes kind of take over. But I think that that will happen. It seems to me that it has legs. It's not like some other movements that sputter out after a while. Anything else? Yes?
When you were talking about nuclear energy, it seemed like you were primarily focusing on the conventional fuel cycle. You did not say much about the fast fission reactor.
No, that's right.
Could you comment on that, how you see that moving?
So the question was, what about unconventional nuclear fuel opportunities like breeder reactors or reprocessing the fuel and use it twice and so on? There are lots of opportunities there. And I think that's not really, at this moment, a science and technology question, but a political one. So quite a long time ago, the U.S. government made the decision that it would not reprocess fuel. Instead, it would just keep it. And they did that to prevent proliferation, because they were worried that weapons would spread. So maybe it's time to look at that again. And as I said, I don't think that's a science question. We know how to build breeder reactors and how to reprocess that fuel and how to get, let's say 5 times or even 10 times the life and the energy out of a given fuel rod than we do now. But we're not doing it for what we think are very good reasons. So that's a world situation. So back in those days, superpowers were confronting each other. Now it's not superpowers, it's terrorists. It's a different situation, still a nuclear problem. But one needs to look at that and see, in the light of the energy problems that we're facing now and that we were not facing, let's say, 10 or 20 years ago, should we do something more with nuclear. And that's not a question, you know, nuclear's been around since 1960. We know how to do it, unlike photovoltaics or even wind, which we sort of know how to do, but not so well, and other technologies, biofuels. We know how to do nuclear. We could just do it. And we've decided so far not to. I think that's another situation, another question that we voters, we private citizens, are going to determine. Because everybody's waiting to see how we feel. And if we say, yes, do it, well, there's lots of people who will do it. Here's a comment.
Yeah. I have a different opinion about that. I think the problem with the nuclear power from a thermodynamic point of view is it is very inherently inefficient because we use the heat. The way to get around it is to make a turbine. Like a nuclear turbine. That way, just like in the gas turbines that we're going to start using for producing electricity, you should be able to get like 50% efficient. How to build it? That's an engineering problem. That's perhaps going to the moon. That's probably which a presidential candidate is supposed. That might be a place to develop, you know, like a nuclear turbine, and really utilize the nuclear energy to its full extent, and that's what we're doing. What we're doing right now.
So that's a very innovative vision, and I totally support it. Let's try to make it happen. You had a question. Oh, you're next. Yeah? Oh, you want me to repeat that? I'm not sure I can repeat the technical part, but he said the problem with nuclear energy is that we're pursuing conventional routes, and we're trying to take it out as heat. We use it to boil water. So why not make a turbine which is run on nuclear energy without the heat? Am I saying this right? And I don't know the mechanism, but...
The ion turbine, which they talk about going to Mars, which is going to decrease the time to Mars travel from a year to a month. I think that would have something in the works on this. So it's not... And I think there was some early research being done on the turbines way back under Eisenhower.
Yeah, these ideas have been around, and they just haven't been funded and developed. You had a question. You. Yeah. You. Sorry.
I have two questions. One, how do you plan to factor in a growing population? Because of course that's open. Two, how do you plan to get these technologies, solar, wind, any of these technologies, to maybe third world countries such as that?
Your first question was about the growing population.
Yeah, how do you plan to factor in
How to factor in the growing population. Yeah. So, okay, it's clear that energy needs are going to go up, and they're going to go up for two reasons. One is population itself is growing, but the bigger reason is that third world countries now expect more energy use than they did. So China is using much more energy than it ever has. India is poised to do that, and lots of other countries as well. So the expectations are growing. And you can do this simple calculation in your head. If the whole world used energy at the rate America does, you would need 4 times the amount of energy to satisfy that need. So that isn't going to happen tomorrow, but you might think of that as an asymptotic limit to the kind of energy demand that's out there. So that's going to create ever more problems. So it'll put stress on traditional fuel sources, fossil fuels, uranium as well, will all get used up faster than we thought. And we're ultimately, I think there's no doubt, the Earth is a finite system, we're ultimately, take 100 years from now, going to have to make a switch to something that is more sustainable than the things which can run out. So how would that happen? I think that's, I don't know how to factor that in, you're asking me, but that's a problem that everybody's going to have to face. And your second question, I think, was how to get these technologies out to third world countries where they're really needed. And I believe that that is something we ought to think seriously about. Most of the developed world, United States, Western Europe, has gone through a certain progression of energy technologies, starting with burning wood and ending up with where we are now. There is no reason for the developing world to go through the same sequence. So just like the developing world doesn't have land phones, they have cell phones, because that makes perfect sense. The same can be true of the energy technologies, and maybe wind ought to be deployed to third world countries or other technologies. We'll go to Africa, for example, where there's no grid. And in fact, interesting number, 1.4 billion people in the world do not have access to an electricity grid. So what do? Well, they burn candles or something else for light. But what if they had a solar cell above their house, and they had an LED light which doesn't require much energy, and they had a computer? Then after dark, the LED light would let people study or work, do things that they need to do. The computer would give a connection to the outside world. It would be a tremendous revolution in opportunity, educational opportunity, communication opportunity, and economic development opportunity. So that is not something you would do in the developed world. You just wouldn't do it. But it can have a transformative effect on certain parts of the third world. So that's my answer.
As far as the global warming and heat transfer.
Yeah, so it's a question of how do you get your heat. And most of these 1.4 billion people that don't have electricity, how do they live? They gather food. They gather fuel. So wood if it's still around, but that's usually been depleted. So they start to take other things that can be burned in household stoves that are tremendously inefficient, that produce a lot of CO and, of course, CO2 and other toxins. And they also produce particle matter. It's unburned stuff, which goes out into the local atmosphere and eventually somewhere. And that, because the number of people doing that is so large, is in fact a big impact. And so you would like to modernize in some way. So just making a better stove that was inexpensive and would not produce the soot and would use less fuel, that would be a huge thing. It's a little bit like the solar cell, the LED, and the computer in Africa. It's the same situation. It's a different solution, not appropriate for the developing countries.
The claim was, as I remember, that this was more important to go after than all we're doing now about energy and that.
So
it doesn't remain in the atmosphere as long.
Yeah.
It's sort of methane, soot that
Can come down.
can come down.
Yeah. So that's a perfect example of a question that has many answers to it, and the answer you favor depends on where you live and the impact on you and maybe your intellectual point of view. And I don't think we're ever going to definitively answer those things. We need more communication, and in some areas it will be clear that this is the route we should take, and in other areas it won't work. But I think that's that's the educational process, the energy literacy process that we need to go through. You had a question.
My point is, sustainability also needs to be providing something positive for the people that are using this energy and also getting something positive out of it. So at the moment we're using corn to produce ethanol, but I think it's kind of like producing Chianti, where there's really not enough land that produces Chianti to satisfy the world's needs and normal Chianti. So we should look at alternatives like the switchgrass, but the switchgrass is probably native to, like the Central Plains and to maybe to our area. And what about like sugarcane? Sugarcane is a crop that will grow fabulously in Haiti, which is the poorest, impoverished country in the Western Hemisphere. And so we could be, growing all that sugarcane there, and for cellulosic ethanol, and
Solving a lot of problems at one time. Yeah.
information on sugarcane and
Sugarcane is it's a wonderful thing, and Brazil has shown that it works great for ethanol, right? It's efficient. It's much higher efficiency than corn ethanol or even cellulosic. Oh yes, 8% is some of the numbers that you hear because of the way the sugarcane plant is constructed. That's the way it operates. I mean, that's its sort of internal system. Yeah, it won't grow in the United States. At least not to the level that it grows in Brazil. And so you need a tropical place for it to grow. And why not propagate that model elsewhere? Well, of course you can. I think there are other countries that are starting to take note that you can do that.
is there any initiative in the United States to have this, crop growth, in Haiti, or for example, Haiti, which is such in dire straits?
I'm not aware of that, and that doesn't mean it's not there. But I could well imagine that there's not much motivation for the United States to get involved because it doesn't affect the United States so much. So, that's a statement some of you, I'm sure, will find provocative. But But that's worth discussing, absolutely. I think your idea is right on target. Oh, because of fracking, yeah. Well, that's a huge topic of conversation and issue. So, yeah, the growth is fantastic. And if you look at the price of natural gas, it's come down dramatically in 2 years. And if you look even more dramatic is the increase in reserves or expected reserves. So every year for the last 5 years, the reserves of methane have gone up, what we claim are the reserves. We don't really know if that's right, but it looks like by fracking, you can get much more methane. And in fact, this country, people say, may become a net natural gas exporter instead of a net natural gas importer, simply because of the shale gas that you get by fracking. So there's no doubt that it's going to change the equation of energy supply and demand. Now, there are some issues, environmental ones, which we all know what they are. They need to be addressed. But it looks like, it's a little bit like nuclear energy. I shouldn't put them in the same box. But there's a great benefit and also a great potential detriment at the same time. Yeah, I need another slide for that. That's something that's only become clear in the last, 3 years, 4 years? Before that, no one was talking about it. It's a technology advance, and it has dramatic impact. So that's a very good. I think, yeah.
Maybe one more question.
Okay. Who will it be? Yes. So to repeat that question, what about energy independence? Is it an achievable goal with all the fluctuations in the world situation and the changes from one administration to another in the United States?
Because it seems to me that each administration has their own...
Yeah, ideas. So what a good question. Here's a brief answer. When you say energy independence, you really mean oil. That's what people mean. And that graph that I showed depicts that. So could you do something about that? And I was reading a very interesting book called, what's it called? It's called, I'll tell you the subject. It was about energy policy in the 1990s. And what they were going through for energy independence. So 20 years ago, the same question was there. And it was thought of very differently. Like we should try to do something to get off foreign oil. 20 years later, we're still not off it. And is there something that can be done? The things that are being asked to be done or being suggested to be done now are very different from the things that were suggested to be done then. And there is an opportunity. It's going to depend. I mean, I didn't talk at all about conservation or using less. The U.S. uses twice the energy per capita that Europe or Japan does. There's a reason for that. I'm not quite sure what it is. Lots of people argue about it. But you could use less, so that would get off foreign. And you could use other things like electricity, which is domestic. It has to be domestic. It's produced domestically. So if you fueled all the car fleet in the United States by electricity, you'd be off foreign oil. There is no doubt about it. People were not saying that 20 years ago. So I think there are opportunities. You don't want to go too far. Actually, Canada is the biggest supplier of foreign oil to us, and we don't mind buying oil from Canada. We get benefit from the money we send to Canada. Some of it comes back to the United States in economic activity, unlike some other countries. So you don't want to go too far. And if you would, instead of 60% of our oil coming from foreign sources, if it were 40%, or 30%, maybe that's a reasonable goal.
But thank you so much for the wonderful presentation.